A star that vanished without a trace challenges everything we know about the cosmos. These stellar anomalies are not just cosmic glitches, they are profound puzzles that force us to rewrite the rules of physics. By the end of this journey, you will understand the 25 most baffling stellar mysteries and what they reveal about the fundamental nature of reality. We will investigate a star that dims in ways that suggest alien engineering and confront the unnerving silence that questions our place in the universe. What single cosmic mystery do you believe could change our understanding of existence itself? A stellar anomaly shatters our expectations of how the cosmos should behave. It is a star or a cosmic event that dramatically breaks the rules written by our best astrophysical models. You can think of it as the universe presenting a puzzle that our current science simply cannot solve. This is not about a minor miscalculation or a blurry telescope image. These are profound deviations, like a star that flickers in a pattern no natural phenomenon can explain, or one that vanishes from the sky without a trace. When astronomers encounter a true anomaly, they are not just looking at a data point, they are staring directly at a flaw in our understanding of physics itself. The criteria for these cosmic outliers are specific. Scientists look for bizarre and irregular dips in a star's light, which could hint at orbiting structures or unknown cosmic weather. They search for unexplained energy emissions, bursts of radiation that seem to come from nowhere. They track motions that defy gravitational logic, like stars moving too fast or in the wrong direction entirely. Each of these strange signatures is a clue. The relentless pursuit of these clues has historically led to our greatest discoveries. The search for one star's wobble revealed the first planets orbiting other suns. The investigation of a strange, repeating signal unveiled the existence of pulsars. Every anomaly is a potential doorway to a new chapter in astronomy. With this foundation of what makes a star truly strange, we are ready to confront the first and most iconic of these cosmic mysteries. In 2015, the Kepler Space Telescope's data revealed a star behaving so strangely it seemed to defy all logic. KIC 8462852, now known as Boyajian star, was caught in the act of fading. Its light did not dip in the gentle, predictable rhythm of an orbiting planet. Instead, it plummeted in chaotic, dramatic plunges, with its brightness sometimes falling by an astonishing 22%. This was not a slight dimming. It was as if something colossal and irregular was passing in front of the star, blocking its light in a way never before witnessed in the cosmos. The initial discovery came not from a team of professional astronomers, but from citizen scientists participating in the Planet Hunters project, ordinary people scanning data for extraordinary patterns. Their find ignited a firestorm of speculation. The first and most natural explanation was a massive swarm of comets, a family of icy bodies breaking up and casting vast shadows. Yet the sheer scale and irregularity of the dimming made even this idea seem strained. This led to a more speculative yet captivating theory. Could we be seeing the signature of alien engineering, a partially constructed Dyson sphere, a vast array of energy-collecting structures orbiting the star? The very possibility sent a ripple of excitement through the scientific community and the public alike. Subsequent observations have scrutinized Boyajian star, ruling out some of the simpler explanations like dust from asteroid collisions. But a definitive answer remains elusive. The star continues its bizarre performance, with each new dimming event carefully recorded, each one adding another layer of complexity to the puzzle. This single anomaly did more than just baffle astronomers. It captured the global imagination, demonstrating how one strange data point can propel scientific inquiry into uncharted territory, forcing us to question what we consider possible. If a star can flicker so mysteriously, what does it mean when one simply blinks out of existence entirely while Boyajian's star flickers in its strange and unpredictable dance? Some stars take this cosmic defiance a step further. They simply vanish. Throughout history, astronomers have meticulously charted the heavens, treating the star maps as a largely permanent record. Yet, occasionally, a star recorded in an old survey is just gone when modern telescopes look for it. It leaves behind an empty patch of sky, a celestial missing persons case with no note and no explanation. The vanishing and appearing sources during a century of observations project, known as VASCO, has made this search its mission. By systematically comparing historical photographic plates with contemporary sky surveys, this project hunts for the ghosts of stars, for points of light that have simply winked out of existence. The implications of finding a truly vanished star are staggering. Our entire understanding of stellar life cycles says this should not happen. Stars are not light bulbs that can be switched off. They live for millions or billions of years, and when they die, they do so spectacularly, in supernova explosions that can outshine entire galaxies. So what does it mean when a star just disappears without that final, violent farewell? One compelling theory is a failed supernova. In this scenario, a truly massive star at the very end of its life might skip the explosive finale altogether. Instead of blowing its outer layers into space, it could collapse directly into a black hole, its light and matter swallowed so quickly and completely that it simply vanishes from our view. One moment it is there, a beacon in the dark. The next, there is only a gravitational tomb. Other, even more exotic possibilities exist. Could some stars collapse into theoretical objects like quark stars, composed of an ultra-dense state of matter that emits almost no light? Each vanished star represents a potential revolution in astrophysics, a silent testament to stellar death processes we have not yet witnessed or even imagined. This search for what is missing fundamentally challenges our perception of a stable, predictable cosmos. It hints at a universe far more dynamic and violently creative than we ever suspected, where stars can be erased from the sky in an instant. And if stars can disappear without a trace, what of those that explode with a power that seems to defy all known limits? But if the quiet disappearance of a star is one extreme, the cosmos is equally capable of the opposite. In the same year, astronomers were puzzling over Boyajian's star. Another celestial object erupted with a violence that redefined the word explosion. Designated Assassin 15LH, this event was not a subtle dimming or a silent vanishing. It was a detonation of almost incomprehensible power, a flash of light so brilliant it was recorded as the most luminous supernova ever witnessed by humanity. At its peak, this single object shone with the light of nearly 600 billion suns like our own. That is more light than every star in our entire Milky Way galaxy combined, emanating from one single point in space. This was not just a bright supernova, it was a superluminous supernova, an event so energetic it shattered the conventional models astronomers used to explain stellar deaths. Normally, a supernova is powered by the radioactive decay of elements forged in the star's final moments, like a cosmic battery slowly discharging its energy. But for Assassin 15LH, that simple battery was utterly insufficient. The sheer energy output was too vast, too sudden, to be explained by any known radioactive process. It was like trying to power a major city for a year with a single firecracker. the only way to explain such staggering luminosity was to propose engines of destruction far more exotic. One leading theory pointed to the birth of a magnetar, a neutron star spinning at an incredible speed and possessing a magnetic field trillions of times stronger than Earth's. The rapid slowdown of such an object could, in theory, convert its rotational energy into the blinding light we observed. Another, even more violent idea was that this was not a supernova at all. Perhaps a star wandered too close to a supermassive black hole lurking in the heart of its galaxy. The black hole's immense gravity would have shredded the star, stretching it into a stream of incandescent gas in a tidal disruption event. The friction and heat as this stellar debris swirled into the black hole's maw could have produced the phenomenal flash. The debate over what actually caused Assassin 15LH continues to this day, a testament to the fine line between different kinds of cosmic cataclysms. This single event forces us to confront the upper limits of stellar violence, revealing that there are explosions in the dark that dwarf our wildest imaginings. And sometimes the universe does not send us light, but a signal etched into the very fabric of space and time. While the cosmos can erupt in flashes of light and violent explosions, some of its most puzzling messages arrive not as a cataclysm, but as a whisper on the radio. Fast radio bursts are exactly what their name suggests. They are incredibly brief, intensely powerful blasts of radio waves that flash into existence for just a few thousandths of a second, often releasing more energy in that instant than our sun does in 80 years. For a long time, these were seen as cosmic one-hit wonders, mysterious and isolated events that appeared and vanished forever. Then, astronomers found one that talked back. FRB 121102, known as the repeater, shattered the single burst pattern. This was not a solitary cry in the dark. It was a source that chattered, emitting hundreds of bursts over time, each one a millisecond-long shriek of radio energy. This repetition was the key that unlocked the mystery, allowing scientists to do what was once thought impossible. They pinned down its home, tracing its origin to a tiny, turbulent dwarf galaxy more than 3 billion light-years away. That location held another vital clue. The repeater was sitting right next to a persistent, quieter source of radio waves, suggesting it was living in an extreme environment, like the neighborhood of a supermassive black hole or within a powerful nebula. The leading suspect for the repeater itself is a magnetar, the same type of ultramagnetic neutron star theorized to power superluminous supernova. Imagine a stellar corpse spinning rapidly, with a magnetic field so unimaginably strong that it can literally twist the star's crust. These magnetic starquakes could be launching the tremendous bursts of energy we detect across the cosmic void. Yet, the precise mechanism that can focus such power into such brief, bright, and repeating signals remains one of astrophysics' greatest debates. The very fact that it repeats forces us to confront a universe that is not just randomly violent, but one that can produce persistent, rhythmic phenomena. This enigmatic repeater is more than just an anomaly. It is an ongoing dialogue, a cosmic laboratory that allows us to test the limits of physics under the most extreme conditions imaginable. But for every persistent signal the universe offers, there is a counterpart of profound and unsettling silence. The universe is filled with the echoes of stellar explosions and the chatter of repeating radio bursts, yet one profound silence echoes louder than all the noise. It is the silence of an apparently empty cosmos, a quiet that stands in stark opposition to everything we believe about probability. This is the Fermi Paradox, a cosmic anomaly defined not by what we have found, but by what we have not. With billions of stars in our galaxy and trillions of planets throughout the cosmos, the statistical likelihood of other intelligent life seems almost a certainty. Yet when we listen, we hear nothing but the natural hum of the universe. The physicist Enrico Fermi captured this contradiction perfectly with his famous, almost plaintive question, "Where is everybody?" Why does a cosmos so vast and so ancient feel so utterly empty? This is not a simple question. It is a fundamental challenge to our place in the universe. One of the most unsettling proposed answers is the concept of the Great Filter. This is a hypothetical barrier, a wall that life or intelligence inevitably hits and cannot surpass. Perhaps the evolution of complex technological civilization is so astronomically rare that it has only happened once, right here on Earth. The filter could lie in our past, a step like the emergence of DNA or multicellular life that is far more difficult than we realize. Or, more chillingly, the Great Filter could await us in our future. It might be that every advanced civilization eventually discovers a technology, perhaps in physics or artificial intelligence, that inevitably leads to its own destruction. The silence we hear could be the silence of countless graveyards. Other resolutions are less bleak but equally mind-bending. Maybe intelligent life is common, but it evolves in forms so alien that its signals and structures are completely unrecognizable to us. Their cities or communications might be built from dark matter or operate on timescales of millennia, making them invisible to our fleeting observations. Or perhaps they are out there, but they have chosen to remain quiet, observing a cosmic rule of non-interference in a universe they know to be far stranger and more dangerous than we can imagine. This cosmic silence is the ultimate anomaly of absence. It is a missing piece of data that speaks volumes, forcing us to confront the unnerving possibility that we are truly alone, or that the universe holds secrets about life's fragility that we have yet to learn. This contemplation of silent, empty space makes the discovery of any potential life, even in the most hostile environments, feel like a revolutionary event. The profound silence of the cosmos makes the faintest whisper of a potential biosignature feel like a shout. On the dusty, rust-colored plains of our neighbor Mars, scientists have been chasing one such elusive whisper for years. It is the ghost of methane, a simple gas that should not be there, appearing and vanishing in a pattern that defies easy explanation. NASA Curiosity rover, a robotic geologist trundling through Gale Crater, has repeatedly sniffed the thin Martian air and detected sudden, unpredictable spikes of methane. These are not constant background levels. They are brief, mysterious plumes that appear and then dissipate, as if someone is periodically opening and closing a tiny valve deep underground. The intrigue lies in what methane represents. On our own planet, the overwhelming majority of methane is a waste product of life, belched by cows and produced by microbes in swampy marshes. Its presence on Mars immediately raises the electrifying possibility of extant life, of Martian microorganisms breathing and metabolizing right now beneath the frozen, radiation-scoured surface. Yet, this detective story is filled with conflicting evidence. The European Space Agency's Trace Gas Orbiter, a sophisticated satellite designed specifically to analyze the Martian atmosphere, has often looked down and found nothing. It has failed to confirm the very plumes the rover on the ground insists are there. This contradiction is not a simple case of one instrument being wrong. It suggests the methane releases are incredibly localized and transient, vanishing before they can spread high into the atmosphere for the orbiter to see. The plot thickens when we consider that biology is not the only suspect. A purely geological process called serpentinization, where certain rocks react with water deep underground, can also produce methane. So the mystery becomes a cosmic courtroom drama. Is the defendant the methane gas, a product of living processes, or is it merely the result of complex, abiotic chemistry we do not yet fully understand? The sporadic nature of the plumes is the key piece of evidence that does not fit neatly into either box. If it is geology, why is the release so burst-like and unpredictable? If it is biology, how are these microbes surviving, and why do they release their gases in such fleeting puffs? This ongoing puzzle on Mars demonstrates how a single anomaly can sit squarely at the intersection of geology and biology, forcing us to question what truly constitutes a sign of life. It is a reminder that the search for our cosmic neighbors may not begin with a distant radio signal, but with the faint, confusing scent of a gas on the world next door. And if a thin atmosphere can hide such profound secrets, what mysteries might be concealed beneath the ice of a frozen moon, far from the sun's warmth, in the frigid darkness of the outer solar system? Entire oceans are hiding in plain sight. Jupiter's moon, Europa, appears as a cracked, icy marble, its surface scarred by a web of reddish-brown fractures. This is not a dead, frozen ball. The very texture of its shell, a mosaic of broken and reformed ice, screams of a world with a churning, liquid heart. Scientists are virtually certain that a global saltwater ocean, containing perhaps twice the water of all Earth's oceans combined, sloshes beneath that icy ceiling. The same incredible story unfolds at Saturn's small, brilliant moon Enceladus. Here, the evidence is even more dramatic. The Cassini spacecraft did not just infer an ocean. It flew directly through giant plumes of water vapor and ice crystals that erupt hundreds of miles into space from fractures at the South Pole. This moon is actively coughing its subsurface ocean out into the void for us to sample. The existence of these vast, life-giving bodies of water so far from the sun is a profound anomaly. It shatters the classic idea of a habitable zone, the narrow orbital band where a planet is just the right temperature for liquid water. These moons receive almost no solar warmth. Their energy comes from within, generated by a constant gravitational tug of war. As Europa and Enceladus orbit their giant planets, the immense gravity flexes and squeezes their interiors, creating enough friction heat to melt rock and maintain a global ocean against the deep freeze of space. This revelation transforms these icy worlds into the most promising targets for finding life beyond Earth. Their dark oceans are not stagnant. They are likely in contact with rocky, hydrothermal vents on the seafloor, chemical-rich environments that on Earth teem with life entirely independent of sunlight. The anomaly is no longer just the presence of water where it should be frozen solid. It is the possibility that the most common abodes for life in our universe are not Earth-like planets orbiting sun-like stars, but these dark, submerged realms orbiting gas giants. We search the galaxy for alien signals, yet the greatest discovery of all might be waiting, silent and hidden, right in our own cosmic backyard. But if these moons hint at biological possibilities, the next stellar mystery suggests something far more artificial, a star that seems to have been built rather than born. The idea of an alien megastructure orbiting a distant star began as a whisper on the edge of science and quickly became a roar in the public consciousness. When Boyajian's star and its bizarre dimming patterns were first discovered, astronomers did what they always do. They ran through the catalogue of natural explanations. A swarm of comets, a cloud of planetary debris, a complex dance of interstellar dust. But the star's light curves were so deep, so irregular, and so unlike anything ever seen, that each natural model seemed to fall just a little bit short. It was in this gap of uncertainty that a truly extraordinary hypothesis found space to breathe. What if we were not looking at a natural object, but at a technological one? The concept of a Dyson sphere, a vast array of energy-collecting panels or habitats constructed by a Type II civilization to harness the entire power output of its sun, was suddenly on the table. This was not the official conclusion of the scientific team, but rather a tantalizing, last-resort possibility they openly acknowledged. The world latched onto it. The alien megastructure star became a global sensation, a story that blurred the line between hard science and science fiction. This public fervor forced a crucial and difficult conversation within the scientific community. How do you prove a negative? How do you definitively rule out intelligence as a cause? Astronomers were pushed to draw a clear line in the cosmic sand, to define what exactly would constitute a technosignature, a sign of technology, versus just an exceptionally weird natural signature. They began to ask new questions. Would an alien megastructure block specific wavelengths of light in a recognizable pattern? Would it emit waste heat in the infrared that we could detect? The very act of searching for answers to these questions refined our entire approach to the search for extraterrestrial intelligence. Over time, as more data poured in from telescopes like Hubble, the balance of evidence began to tilt away from the megastructure. Detailed analyses of the dimming light suggested it affected different colors in ways more consistent with fine dust than solid panels. The leading explanation today points towards a complex family of exocomets, breaking up and casting vast, irregular shadows. Yet the case is not entirely closed. The star continues to behave strangely, and no single model explains every single dip with perfect certainty. The true legacy of Boyajian's star is not a confirmed alien civilization, but a profound lesson in scientific humility. It showed how a single, stubborn anomaly can force us to confront our own assumptions, to entertain the wildest of ideas in order to better test them, and to improve our tools for the next great mystery. The most exciting answer is rarely the correct one, but the pursuit of it often leads us to a deeper, more nuanced understanding of the cosmos. That pursuit leads us from the hypothetical construction of a civilization to a natural object so precise it could be mistaken for one. Sometimes the universe sends a signal so perfect it feels like a message. In the autumn of 1967, a young postgraduate student named Jocelyn Bell Burnell was reviewing data from a radio telescope she had helped build. She noticed a tiny, persistent bit of scruff on the chart paper, a signal that did not look like the random cosmic static she was accustomed to. It was a series of pulses, arriving with a rhythm so precise and unvarying it seemed almost mechanical. Every 1.33 seconds, like cosmic clockwork, this invisible object in space ticked. The regularity was astounding. The team, half in jest and half in genuine bewilderment, labeled the source LGM-1 for little green men. They had to seriously consider the possibility that they were listening to a beacon, an interstellar transmitter built by an advanced civilization. The truth, when it finally emerged, was almost as strange as little green men. They had discovered the first pulsar, a type of star previously only theorized. A pulsar is the collapsed core of a massive star that has exploded in a supernova. This stellar corpse, a neutron star, is so incredibly dense that a single teaspoon of its material would weigh billions of tons. Spinning at incredible speeds, it throws out beams of intense radiation from its magnetic poles. If one of those lighthouse-like beams sweeps across Earth, we detect a pulse with every rotation. What felt like an artificial signal was the heartbeat of a natural cosmic engine of unimaginable power. This discovery was not just a solved mystery, it was a revolution. Pulsars provided the first direct evidence for the existence of neutron stars, confirming a key prediction about stellar evolution. The study of these objects opened an entirely new window into the most extreme states of matter in the universe, earning a Nobel Prize. the story of LGM-1 is a timeless lesson in scientific humility. It reminds us that our first interpretation of an anomaly is often a reflection of our own hopes and fears. When faced with the truly unknown, nature's reality is frequently more wondrous than our imagination. For every cosmic object with perfect rhythm, however, there is another that thrums with chaotic, unpredictable energy. A star in flight paints a portrait of cosmic violence. Zeta Ophiuchi is a behemoth, a hot blue giant racing through the galaxy at 67,000 miles per hour. As it plows through the thin gas and dust between stars, it does not slip through silently. Its passage creates a spectacular, arcing wave in the interstellar medium, a cosmic bow shock that glows with infrared light, like the wave pushed ahead of a ship moving at impossible speed. This is a runaway star, and its incredible velocity is the central mystery. How does a star, an object of immense mass, get thrown across the galaxy like a stone from a sling? The most compelling theory reconstructs a stellar catastrophe. Astronomers suspect Zeta Ophiuchi was not always alone. It was likely once the smaller partner in a binary system, locked in a gravitational dance with an even more massive star. That partnership ended in a cataclysm. When the more massive star exhausted its fuel, it did not die quietly. It collapsed and exploded as a supernova. This detonation was so violent that it effectively blew the binary system apart. The exploding star was obliterated, and in that instant, the gravitational bond that held Zeta Ophiuchi in orbit was severed. The surviving star was suddenly flung away, catapulted by the force of its partner's death, sent careening across the galaxy on its new, solitary path. The existence of such runaway stars is more than just a dramatic story. It provides crucial evidence for the turbulent life cycles within dense star clusters. These stellar nurseries are chaotic environments where gravitational interactions and supernova explosions are common, and stars like Zeta Ophiuchi are the living proof of that violence. They are the shrapnel from cosmic explosions, and by tracing their paths backwards, astronomers can piece together the history of these ancient cataclysms. This drama of stellar escape forces a fascinating question. If one star was flung away, what was left behind in its wake? The supernova's core must have collapsed into something, a dark and dense remnant lurking in the silence from which the runaway fled. The invisible scaffolding of the cosmos has just been pulled away. For decades, the prevailing model of the universe has rested on a simple, powerful idea. Dark matter, that mysterious and unseen substance, acts as a gravitational anchor, its immense pull holding galaxies together and dictating how they spin. Without this dark glue, our models say, galaxies should simply fly apart. Yet one galaxy, known as NGC 1052DF2, defies this universal rule. It appears to contain almost no dark matter at all. This discovery was not just unexpected. It was deeply unsettling, like finding a building standing tall with no foundation. The velocity of the stars and globular clusters within this ghostly galaxy revealed its secret. They were moving too slowly. If dark matter were present in the amounts we see everywhere else, its gravity would be whipping those stars into a much faster dance. Their leisurely pace means only one thing: the invisible giant is missing. This presents a paradox that cuts to the core of astrophysics. If dark matter is essential for galaxy formation, how did a galaxy form without it? One compelling theory suggests a violent past. Perhaps this galaxy was once normal, but a catastrophic collision with another galaxy ripped away its dark matter halo, leaving the visible stars behind like driftwood after a tidal wave. Another, more radical idea is that our understanding of gravity itself is flawed. Maybe on certain scales, gravity behaves differently than Einstein predicted, eliminating the need for dark matter entirely. The existence of this one strange galaxy proves that our cosmic models are incomplete. The absence of something we cannot see has become one of the most telling clues in modern astronomy, forcing us to question the very fabric of the cosmos. Our entire galaxy is caught in a relentless river of motion, pulled by a hidden force. The Milky Way, along with our entire local group of galaxies, is not drifting aimlessly through the cosmos. We are all racing at a staggering 1.3 million miles per hour toward a specific, mysterious point in the constellation of Centaurus. This destination has a name that sounds like something from science fiction, the Great Attractor. It is a colossal gravitational anomaly, a region of space so dense with matter that its pull dominates the motion of countless galaxies for hundreds of millions of light years around us. The frustrating part is that we cannot see it directly. The Great Attractor lies hidden behind the thick veil of stars and dust in the plane of our own Milky Way, obscured by the very galaxy we call home. For decades, this unseen giant was the sole suspect for our cosmic journey, but the story is more complex than a simple pull. Imagine trying to understand why a leaf is floating down a stream. You might first look at the waterfall pulling it forward, but you must also consider the calm pool behind it, pushing it away. This is the second half of our motion. Astronomers now believe we are not just being pulled, but also pushed. The force behind this push is not an object, but an absence. They call it the Dipole Repeller, a vast billion-light-year-wide cosmic void, an underdense region of the universe that is remarkably empty. In this grand cosmic tug-of-war, the dense concentration of the Great Attractor pulls us in, while the immense emptiness of the Dipole Repeller effectively pushes us out. Gravity works both ways. While a massive cluster of galaxies pulls matter toward it, a giant void, lacking the gravitational pull to hold things, allows the space around it to expand more freely, creating a relative push from that direction. Our observed velocity is the net result of this push and this pull. This revelation transforms our understanding of the cosmos on the largest scales. The universe is not a uniform soup. It is a vast cosmic web, a labyrinth of glittering filaments where galaxies cluster, connected by threads of dark matter and separated by immense dark bubbles of near-nothingness. Our motion is a single clue that points to this entire structure, a structure built from both what is there and what is not. This flow of galaxies is a testament to the distribution of all matter, both the visible stars and the invisible dark matter that binds it all together. If the push and pull on our own galaxy feels immense, it hints at structural anomalies of an even greater, more bewildering scale. Even the universe's most fundamental numbers are now being questioned. The Hubble tension is a quiet crisis brewing in cosmology, a disagreement over a single, crucial number that describes how fast everything is flying apart. This number is the Hubble constant, the current rate of the universe's expansion. The problem is that we get two different answers depending on where we look. When we peer back to the universe's infancy by studying the faint afterglow of the Big Bang known as the cosmic microwave background, we get one value for this expansion rate. It is a pristine measurement from a time when the cosmos was simple and smooth. Yet, when we measure the modern, local universe using reliable cosmic mile markers like Cepheid variable stars and supernova, we get a different, faster rate. The two results do not just differ slightly, they are discrepant enough that the chance this is a simple error is vanishingly small. This is not a matter of fuzzy data. It is a fundamental crack in the foundation of our cosmic model. The entire framework of modern cosmology, known as the Lambda-CDM model, is built on a specific set of ingredients, including dark energy and dark matter. This model has been spectacularly successful at describing the universe's history, but the Hubble tension suggests the model is incomplete. It might be missing a key ingredient, something that acted in the early universe or is acting now to change the expansion rate. What could this missing piece be? Perhaps dark energy, the force driving the expansion, is not constant but has been evolving over time, growing stronger or weaker in a way we have not accounted for. Maybe neutrinos, those ghostly particles that stream through everything, have unexpected properties like a subtle mass that influences the cosmic growth. Or, most radically, our understanding of the physics of the very first moments after the Big Bang could be flawed. Resolving this tension is one of the primary goals for the James Webb Space Telescope and other next-generation observatories. They are not just looking for new stars or galaxies. They are on a mission to perform a cosmic audit, to check the universe's math and find where our calculations went wrong. This disagreement on the grandest possible scale proves that even our most successful scientific stories are not finished. They are living documents, constantly being revised by the stubborn, contradictory voice of the cosmos itself. A supermassive black hole should be the anchor at the heart of its galaxy, an unmoving giant around which everything else revolves, but the universe has a habit of breaking its own rules. Through the keen eye of the Hubble Space Telescope, astronomers have found black holes that are not anchored at all. They are cosmic wanderers, adrift within their own galactic cities, displaced from the central core. One of the most striking examples lies in a galaxy with the unpoetic name SDSSJ 1126+2944. Here, observations revealed not one, but two supermassive black holes. One sits where you would expect it, at the galactic center. The other is a nomad cast out into the galactic outskirts. This second black hole is described as naked, having been violently stripped of the dense cocoon of stars that typically surrounds these behemoths. The story this tells is one of incredible violence. This galaxy is the product of a catastrophic merger, a collision between two separate galaxies, each with its own central black hole. As the galaxies spiraled together and combined, their two black holes began a gravitational dance, swinging around each other in a tightening orbit. In this chaotic process, the smaller black hole was likely flung out from the core, a celestial billiard ball sent careening by the immense gravitational forces at play. The very stars that once cloaked it were ripped away, leaving behind a bare, wandering singularity. This discovery challenges the serene picture of a quiet black hole at the center of every galaxy. It shows that galaxy assembly is not a gentle process. It is a brutal, messy affair that can leave the most powerful engine of a galaxy displaced, cast out into the stellar suburbs. These rogue black holes are direct evidence of the dynamic interplay between a black hole and its home, proving that even the universe's most dominant objects are not immune to the chaos of cosmic collisions. They are the ghosts of ancient mergers, and their lonely journeys help us map the violent history of galaxy formation. If a merger can tear a black hole from its home, what other monstrous creations could such violence forge? A visitor from the void arrived without warning. In October 2017, the Pan-STARRS telescope in Hawaii spotted a strange point of light moving at incredible speed. This was no ordinary asteroid from our own solar system. Its trajectory was hyperbolic, a path so extreme it could only mean one thing. The object, soon named Oumuamua, which in Hawaiian means a messenger from afar arriving first, was an interstellar traveler, the first ever confirmed visitor from another star system. As it hurtled away from the sun, astronomers scrambled to learn everything they could about this cosmic tourist. What they found only deepened the enigma. Its shape was the first shock. Based on its extreme changes in brightness, Oumuamua appeared to be highly elongated, perhaps 10 times longer than it was wide, tumbling end over end through space. This cigar or pancake-like form was unlike any asteroid or comet we had ever seen in our own cosmic backyard. Then came the real puzzle, its acceleration. As Oumuamua departed, it did not follow a path dictated by the sun's gravity alone. It sped up slightly, an extra push known as non-gravitational acceleration. Comets do this all the time, but through a visible process called outgassing. As the sun heats a comet's icy surface, it vents gas and dust, forming a glowing coma and a tail that acts like a natural rocket engine. Yet Oumuamua showed no coma, no tail, no visible debris whatsoever. It was accelerating in utter silence. This invisible thrust forced scientists to consider exotic possibilities. Could it be venting pure hydrogen gas, which would be invisible to our telescopes? Or was the acceleration due to the subtle pressure of sunlight itself pushing on an object of exceptionally low density, like a cosmic dust bunny? The lack of a simple, visible explanation, however, opened the door to a far more speculative idea. Could this acceleration be the signature of a light sail, an artificially constructed panel designed to be pushed by starlight? The suggestion was controversial, but it highlighted just how anomalous this object was. It defied every comfortable category we had. It was not a typical comet nor a standard asteroid. It was a shapeshifter in our data, a tumbling enigma that challenged our very system of classification. By the time we knew enough to be truly baffled, Oumuamua was already too far away, receding back into the interstellar dark from which it came. Its brief passage left behind a profound legacy. It was a single data point that transformed our perspective, proving that interstellar space is not empty. It is filled with unseen wanderers, and some of them are utterly unlike anything we have at home. The ancient light from HD1 carries a message of impossible brilliance. This galaxy, spotted as it was just 330 million years after the Big Bang, is not a faint infant smudge. It blazes with an intensity in ultraviolet light that defies all expectations for such an early time. To shine that brightly, something monumental must be happening inside it. Astronomers are confronted with two equally staggering possibilities, both of which break our established models. The first scenario is that HD1 is a stellar factory operating at a frenetic, almost violent pace. It could be producing stars at a rate 100 times greater than our own Milky Way, burling suns in a furious whirlwind of creation. Imagine an entire galaxy igniting in a single, spectacular flash of stellar birth. The second, even more radical idea is that we are not looking at a galaxy full of young stars, but at the brilliant beacon of a supermassive black hole, one that had already grown to 1 billion times the mass of our Sun in what amounts to a cosmic instant. How could such a colossus form so quickly after the universe began? Its very existence would shatter our understanding of how these gravitational monsters seed and grow, suggesting formation pathways we have not yet dreamed of. Whether it is a frenzy of starlight or the glare from a voracious black hole, HD1 stands as a profound challenge. It forces us to rewrite the story of the cosmic dawn, revealing an infancy far more dynamic and explosive than we ever thought possible. To see this ancient glow is to look back at the universe's first steps and realize they were not a slow crawl, but a dramatic, brilliant sprint. There is a world where mountains might be made of gemstones and shorelines of graphite. Orbiting a sun-like star 40 light-years away, the planet 55 Cancri E is a super-Earth that defies our rocky, water-based perspective. This is not a world built like our own. While Earth is rich in oxygen and silicon, This planet appears to be overwhelmingly composed of carbon. Under the immense pressures within its interior, that carbon is likely compressed into a crystalline structure. A significant portion of this world, which is about twice the size of our own, could be a vast deposit of diamond. Imagine a landscape not of stone, but of glittering carbon, where precious gems are the common bedrock. This diamond planet is also a world of brutal extremes. It orbits so close to its parent star that a full year passes in just 18 hours. Its surface is almost certainly a global ocean of incandescent lava, perpetually scorched by the relentless stellar radiation. The very existence of such a world is a profound anomaly. It demonstrates that the protoplanetary disks from which planets form can have wildly different chemical recipes. Our solar system formed from a disk rich in oxygen, giving us a world of sand and water. But around another star, a carbon-rich disk gave birth to a jewel. This discovery shatters the assumption that all rocky planets will be Earth-like. It opens up a universe of almost alchemical possibilities, where the fundamental building blocks of planets can create environments of unimaginable splendor and fury. From a world that pulses with the heat of a forge, we turn to a star that pulses with a rhythm we cannot yet explain. A cosmic dance of two stars can create a visible, rhythmic pulse across the void. These are the heartbeat stars, a class of binary system discovered by the Kepler Space Telescope that exhibits one of the most strangely beautiful patterns in the sky. Their light curves do not show the simple, repeating dips of a planet transit. Instead, they produce a sharp, dramatic spike in brightness, followed by a gentle, symmetrical decline, tracing a line that looks exactly like a human heartbeat on an electrocardiogram. This pulse occurs with perfect regularity each time the two stars swing to their closest point in elongated orbits. The cause of this brilliant flash is not an external object, but the stars themselves warping under an immense gravitational embrace. As they draw near, their mutual gravity becomes so powerful that it stretches each star out of its comfortable sphere, pulling it into an egg-like shape. This profound distortion has a direct and measurable effect. The increased surface area facing us during this close pass makes the system appear brighter. Furthermore, the same intense tidal forces can actually heat the star's gases, causing a temporary rise in temperature that adds to the brilliant flash. In some of these systems, the gravitational pull is so extreme it sets one star ringing with resonant vibrations, like a bell struck by its companion's gravity. These tidally induced pulsations allow astronomers to peer deep into the stellar interior, using the star's own oscillations to understand their density, composition, and structure. Heartbeat stars are therefore more than just a celestial curiosity. They are a pristine natural laboratory. By observing their precisely timed interactions, scientists can test theories of how tidal forces work over astronomical distances, how energy is transferred between stars, and how these intimate gravitational dances ultimately influence the long-term evolution of binary systems. This elegant, rhythmic phenomenon demonstrates how interconnected cosmic bodies can be, their fates and their very forms locked in a perpetual, visible embrace. This intricate dance of gravity on a stellar scale finds a bizarre parallel in the quantum realm, where the rules of the very small twist the nature of the very large. The universe has a built-in speed limit for the most powerful subatomic bullets. This is the GZK cutoff, a theoretical barrier named for the scientists Greisen, Zatsepin, and Kuzmin. Their work predicted that cosmic rays, which are atomic nuclei hurtling through space at nearly the speed of light, should not be able to travel immense intergalactic distances if their energy is too high. The reason is a faint, omnipresent fog that fills all of space, the cosmic microwave background radiation. This afterglow of the Big Bang is the universe's oldest light, and it is everywhere. When an ultra-high-energy cosmic ray, say a single proton, travels across billions of light years, it should inevitably collide with the photons of this ancient light. Each collision is like a high-speed car crash, robbing the cosmic ray of its energy bit by bit. Over a long enough journey, these countless tiny collisions should grind down even the most energetic particle, ensuring that nothing from a distant galaxy arrives here with an energy beyond a certain limit. The math was clear and the physics seemed sound. Then we started looking. Experiments like the Pierre Auger Observatory, with its vast array of detectors spread across the Argentine plains, began catching these cosmic bullets. To the astonishment of physicists, they found particles that had no right to be here. These ultra-high-energy cosmic rays possess energies millions of times greater than anything produced in our most powerful particle accelerators. A single one carries the kinetic energy of a well-thrown baseball, all packed into a subatomic speck. Their detection is the anomaly, a direct violation of the predicted cutoff. It is as if we found a bullet that had been fired from 1,000 miles away, but had traveled in a straight line without ever hitting a single molecule of air. The existence of these particles forces two staggering questions. Where are these cosmic accelerators, and how do they work? The sources must be phenomenally powerful, capable of focusing energy into a single particle with an efficiency that dwarfs any known natural process. The suspects are the usual cosmic tyrants, like the active supermassive black holes at the hearts of galaxies, or the cataclysmic jets of gamma-ray bursts. Yet, pinning the crime on a specific source is incredibly difficult. These particles are not electrically charged, so their paths are bent and scrambled by the magnetic fields that weave through intergalactic space, obscuring their point of origin. They could be coming from relatively nearby within our local supercluster, from an object we have not yet identified. Or they could be telling us that our understanding of particle physics itself needs a fundamental rewrite on the most extreme energy scales. Each one of these rare, ultra-high-energy events is a messenger from the most violent engines in the cosmos, and we are only just beginning to decode their origin story. The universe's oldest light holds a fossil of profound cold. The cosmic microwave background is the remnant heat from the Big Bang, a nearly uniform glow that fills all of space. Yet within this fossilized echo, one region stands out as a stark and chilling exception. This is the CMB cold spot, a vast area of sky significantly colder than its surroundings, an anomaly so large and so cold it defies easy explanation. This is not a minor statistical fluctuation. The cold spot's size and temperature depression are extreme outliers, pushing the limits of what our standard model of cosmology can comfortably accommodate. One of the leading theories proposes that the light traveling to us from that direction passed through a cosmic supervoid, an immense region of space with far fewer galaxies and clusters than average. As light enters such an underdense region, it must climb out of a gravitational well, losing energy and shifting to a colder temperature in a process known as the integrated Sachs-Wolf effect. The problem is the scale. To cause the observed cold spot, this supervoid would need to be of a size and emptiness that challenges our current understanding of how large-scale structure forms in the universe. It would be a void of voids, a staggering nothingness that seems almost as unlikely as the cold spot itself. This difficulty has given rise to more exotic possibilities, ideas that venture to the very edge of cosmology. Some physicists suggest the cold spot could be a bruise, a relic from a collision with another universe during the period of cosmic inflation. In this mind-bending scenario, our expanding bubble universe might have grazed another, and the energy of that interaction left a permanent scar on the fabric of our cosmos. Whether it is an unprecedented void or a mark from a multiverse, the cold spot remains one of the most hotly debated features of the ancient sky. It is a ghost in the machine of creation, a potential clue that the story we have written about the universe's birth is missing a crucial and perhaps revolutionary chapter. From this fossil imprint at the dawn of time, we turn our gaze closer to home, to an enigma waiting in our own celestial backyard. Our own solar neighborhood holds a cautionary tale of celestial misidentification. Just 25 light-years away, the brilliant star Fomalhaut is encircled by one of the most stunning structures ever seen from Earth, a razor-sharp ring of dust that looks like a cosmic hula hoop. Within that pristine belt, the Hubble Space Telescope captured what seemed to be a triumph, a bright pinprick of light moving in orbit. This was heralded as Fomalhaut B, one of the first exoplanets ever directly imaged. The initial interpretation was perfectly logical. We had a belt of debris and a bright dot moving along a predictable path. It had to be a planet, but the universe loves a good plot twist. Astronomers kept watching, expecting the dot to continue its steady journey. Instead, it began to behave impossibly. The object started to grow larger and fainter, spreading out like a drop of ink in water. A true planet does not expand and dissolve before our eyes. The brilliant candidate, Fomalhaut B, was not a world at all. It was a cosmic mirage. The leading explanation is that we were witnessing the aftermath of a catastrophe. Two infant planetary bodies, each perhaps hundreds of miles across, slammed into one another just before our observations began. The bright dot was the incandescent cloud of vaporized rock and dust from that colossal impact, a cloud so vast it was briefly as bright as a planet. Over the years, this cloud simply continued to expand and dissipate, fading into the background glow of the larger dust belt. This vanishing act is more than just a case of mistaken identity. It is a vivid snapshot of the violent construction zone that is a young planetary system. The dust that makes up Fomalhaut's beautiful ring is the very stuff of creation and destruction, the pulverized remains of countless collisions and the raw material for planets yet to be born. The entire system is a dynamic workshop, not a finished museum piece. The story of Fomalhaut B is a powerful lesson in cosmic patience. It reminds us that a single snapshot in time can be deeply misleading, and that the truth often reveals itself only through the persistent, long-term stare of our telescopes. This dance of creation and destruction around a single star finds a strange echo in the very laws that govern the cosmos, where the rules of the small create a fundamental tension with the reality of the large. The cosmos can sculpt death into a masterpiece of geometry. Glowing deep in the constellation Monoceros, the Red Rectangle Nebula presents one of the most perfectly symmetrical structures ever observed. Its name, drawn from its box-like appearance and intense crimson hue in early images, only hints at its true elegance. This is not a chaotic cloud of stellar debris. It is a protoplanetary nebula, a brief and beautiful phase in the death of a star similar to our Sun, and its form is a direct consequence of the celestial dance at its heart. The central star, known as HD 44179, is not one but two. This binary pair is locked in a tight orbit, and their gravitational waltz is the artist shaping the nebula. As the primary star shed its outer layers at the end of its life, the powerful outflows of gas and dust did not expand in a simple sphere. Instead, they were funneled and focused by the swirling disk of material encircling both stars. The result is two opposed conical lobes of glowing gas that form a stunning X-shape, a structure of such precise symmetry it seems almost engineered. The vibrant red color comes from a specific type of molecule known as polycyclic aromatic hydrocarbons, complex chains of carbon and hydrogen that fluoresce under the intense ultraviolet light from the dying stars. This entire breathtaking spectacle is profoundly transient. The red rectangle captures a star in its final act, expelling its atmosphere before the hot core is left behind to cool as a white dwarf. Within just a few thousand years, the gorgeous lobes will dissipate into the interstellar medium, their raw materials destined to be recycled into new stars and planets. This nebula is a testament to how orbital dynamics can transform a star's death throws into a fleeting work of cosmic art, a reminder that even in endings, the universe imposes an elegant order. Why, then, does one ancient star appear to have cheated this very cycle of death and rebirth? Amidst the ancient stellar cities of globular clusters, a strange population of stars refuses to grow old gracefully. These are the blue stragglers, brilliant and hot stars that shine with a youthful vigor completely at odds with their surroundings. A globular cluster is like a retirement home for stars, a dense ball where hundreds of thousands of stars all formed at roughly the same time, over 10 billion years ago. By now, all the massive, hot, blue stars should have burned through their fuel long ago, ending their lives in supernova. The remaining stars should be aging suns, red giants, and cooling white dwarfs. Yet, scattered among this elderly population are these anomalous blue stars, burning brightly as if they were mere billions of years old. They are stragglers in time, having seemingly evaded the relentless march of stellar evolution. So how do these stars cheat death? The leading theories involve stellar interactions of either a violent or an intimate nature. In the crowded core of a globular cluster, stars can pass perilously close to one another. Sometimes two lower mass stars collide head-on, merging into a single, more massive star. This new composite star is hotter, bluer, and has a fresh supply of hydrogen at its core, effectively resetting its evolutionary clock. It is a stellar phoenix born from a cataclysm. The other primary mechanism is a slower, more parasitic process involving binary stars. In a close binary system, one star can siphon hydrogen fuel directly from its companion. This vampire star gorges itself on this fresh hydrogen, reinvigorating its fusion processes and extending its bright, blue life far beyond its natural span. The donor star is left depleted, a ghost of its former self. These blue stragglers are therefore more than just cosmic curiosities. They are living records of the dynamic social lives of stars in these densely packed environments. By studying their locations and properties, astronomers can map the gravitational interactions and close encounters that shape these ancient clusters. They prove that in the cosmos, a second act is possible, forged either through a catastrophic merger or a slow gravitational theft. This stellar defiance forces us to ask what happens when the most massive stars of all face their own final curtain call. A star can scream its own death without actually dying. This cosmic deception is the hallmark of a supernova imposter, a class of stellar outburst that mimics the brilliant flash of a true supernova but is merely a violent tantrum. The star survives its own apparent cataclysm. One of the most dramatic performers in this strange category is known as SN 2009 IP. For years, this massive star staged a series of spectacular eruptions, violently expelling huge shells of its own atmosphere into space. Each time, astronomers watched as it flared to a phenomenal brightness, a display that seemed to signal its final demise. Yet after each paroxysm, the star remained, its core intact, gathering itself for the next performance. This cycle of false alarms continued until 2012, when SN 2009 IP did something different. Its final outburst was not another imposter event. This was the real thing, a genuinely terminal core collapse supernova that finally tore the star apart. The central anomaly is the engine behind those earlier, non-lethal eruptions. What could cause a star to violently expel so much of itself without triggering its own complete destruction? The leading theories point to periods of extreme instability deep within the star's core. In its final years, a truly massive star can become so luminous that the outward pressure of its own radiation begins to overpower the inward pull of gravity. This can trigger immense episodes of mass loss, where the star literally blows its own outer layers into space in a series of convulsive outbursts. It is a stellar warning system, a prelude to the final collapse. Studying these imposters is crucial because they draw a clear line in the cosmic sand between a major eruption and a true explosion. They teach astronomers to read the warning signs, to understand the final, tumultuous years when a star is fighting a losing battle against its own immense gravity. These false alarms are not failures of observation. They are a key part of the story of stellar death, revealing that the end for the most massive stars is not always a single, sudden event, but often a drawn-out and dramatic series of farewells. This exploration of stellar finales brings us to the edge of physics itself, to a consideration of the very stage upon which all these cosmic dramas unfold. For decades, our cosmic accounting books have not added up. The universe was hiding more than half of its ordinary matter, the protons and neutrons that make up everything we can see and touch. This was not dark matter, but the very stuff of stars, planets, and ourselves, and it was simply missing from our inventory. The numbers from the Big Bang's aftermath told a clear story of how much baryonic matter should exist in the modern universe. Yet when we tallied up all the galaxies, stars, and visible gas clouds, we could only find about 50% of what the theory demanded. Where had the rest of the universe's normal substance gone? The answer appears to be woven into the fabric of the cosmos itself, hidden within the gossamer threads of the cosmic web. This vast, interconnected network of dark matter forms the skeleton of the universe, with galaxies clustering at the intersections of its filaments. For years, these filaments were thought to be mostly empty, mere highways for galaxies to travel. But we now believe they are filled with the missing matter, existing as an incredibly diffuse and scorching gas known as the warm-hot intergalactic medium, or WIM. This gas is so hot at millions of degrees that it glows not in visible light but in faint X-rays. It is so tenuous that a cubic meter of it might contain only a few particles, a vacuum far emptier than anything we can create in a lab on Earth. Detecting this faint, pervasive fog required immense patience and ingenuity, using distant quasars as cosmic flashlights. As the brilliant light of these quasars travels across billions of light years to reach us, it passes through the filaments of the cosmic web. The WIM imprints a faint signature on this light, subtle absorption lines that reveal the presence of highly ionized oxygen and other elements. It is like finding the ghostly silhouette of a nearly invisible structure by the way it dims a distant, brilliant lamp. This discovery closes one of cosmology's most enduring missing person cases. The baryons are not missing. They have been here all along, woven into the grand architecture of the universe, a vast, hot ocean in which all galaxies swim. This resolution is a profound testament to the power of our models, confirming a key prediction of the Big Bang and finally completing our census of the ordinary stuff of creation. We have learned that the universe conceals its greatest treasures not in the brilliant beacons of stars, but in the delicate, heated threads that bind them all together. Having journeyed through 25 of the cosmos's greatest puzzles, from vanishing stars to this hidden cosmic web, a final question remains. What do all these anomalies, these beautiful exceptions to the rules, collectively tell us about the nature of reality itself? These 25 cosmic puzzles reveal a universe that is fundamentally untamed. Each anomaly, from the silent vanishing of a star to the impossible brilliance of an infant galaxy, marks a boundary line for our understanding. They are not evidence that science has failed, but rather proof that it is working exactly as it should. Every strange flicker of light and every inexplicable silence acts as a catalyst, fueling the essential cycle of observation, bold hypothesis, and revolutionary discovery. The cosmos, as these mysteries show us, is a dynamic and often violent arena. Its true rules are not written in the gentle physics of our earthly experience, but in the unimaginable extremes of gravity that can tear a black hole from its home, temperatures that can forge diamond planets, and densities that can make a pulsar's heart harder than steel. Confronting these realities teaches us a profound humility. For every question we manage to answer, the universe seems to pose a dozen more, each more baffling than the last. The common thread running through all these stories is that our current models of physics are not wrong, but they are incomplete. They are powerful approximations of a reality that is consistently stranger, more creative, and more wonderful than we often allow ourselves to conceive. This relentless pursuit of the unexplained is the very engine of astronomy. It ensures that the final frontier will never become mundane, and that our sense of wonder, faced with the sheer scale of what we do not know, will never fade. This collective journey through the cosmos's greatest oddities leaves us with a final, unifying thought about our place in it all. Our journey through these 25 cosmic riddles paints a picture of a universe that is relentlessly creative and defiant of simple explanation. From the strange dimming of Boyajian's star to the profound silence of the Fermi Paradox, each phenomenon is far more than a celestial curiosity. These anomalies are the vital signposts pointing directly toward the next great revolutions in physics and astronomy. They force us to acknowledge that our current understanding is a starting point, not a final destination. The cosmos operates as a vast, natural laboratory, and with these puzzles, we are just beginning to design our first true experiments. The astronomer Carl Sagan perfectly captured this spirit of exploration when he said that somewhere, something incredible is waiting to be known. Let this tour of stellar mysteries be a launchpad for your own curiosity. The next time you look up at the night sky, see it with fresh eyes, knowing that it holds secrets and wonders far beyond our current imagination. We would love to hear which of these cosmic anomalies captured your imagination most powerfully. Share your thoughts in the comments below, and if you are eager to continue this journey of discovery together, subscribe to the channel. The universe's greatest mysteries are still out there, waiting for us to unravel them.